Okay, guys, so I would like us to look at power series method of solving ordinary differential equations. Now, second order ordinary differential equations that cannot be solved by analytical methods, those involving, let's say, variable coefficients, can often be solved in the form of an infinite series of powers of the variable. So in this chapter, we really need to remember the standard differential coefficients. Also remember the binomial theorem and also Maclaurin's theorem. Now, under higher order differential coefficients, a series, we start off with the exponential function. So if we have our y being equal to exponential ax, differentiating it the first time we get a exponential ax, the second time we get a squared exponential ax. So we need to also remember successive differentiation and so on. So if we abbreviate dy dx to be y prime and the 2y dx squared to be y double prime and so on, then we find that our y prime is now a exponential ax, our y double prime is a squared exponential ax, and if we were to continue to y third prime, we would get that it is a cubed exponential ax. So generally, we have y raised to power n or yn prime being equal to an exponential ax, such that if we are to evaluate, let's say, a different function involving the exponential, if you're told y is equal to 3, so taking up an example, y is equal to 3 exponential 2x. So using the general formula, you get y.
For a girls' night. I'm sorry, I did not, and it was an irresponsible last minute thing to do, and I had to hurry.
Okay. So if we need to get the 7y dx 7, then using the general formula, this would be 3 and then 2 raised to power 7. As you can see, a is raised to power 7. So our a here is 2 and then exponential 2x. And this generally gives 38,384 exponential 2x. If you were to take up another example, example 2, so let's have this as our example 1, then example 2, having our y being equal to, let's have our y being equal to 8 exponential t over 2. So what's our d5y dx 5? This will be equal to, so we have our 8 here. Our a is a half raised to the power 5, and then we have exponential t over 2. And this will give 1 over 32 and then 8 divide, therefore. So this will give 1 over 4 exponential t over 2 and so on. So that's for the exponential function. Then we move on to how would we write the sine function? So higher order differential coefficient for sine ax. So if we have our y being equal to an arbitrary sine ax, then what's going to be our y prime? Differentiating this, we will get a cos ax, which is obviously the same as a sine ax plus pi over 2. Differentiating for the second time, y double prime. If you differentiate this, we will get minus a squared sine of ax, okay, which is obviously the same as a squared sine ax plus pi. And this can also be written as a squared sine ax plus 2 pi over 2. What I've done is just to introduce 2 both on the upper side and the lower side. Okay, so this is y double prime. So if you were to get y third prime, this would give us, so differentiating this will be minus a cubed cos of ax, which is the same as a cubed sine ax plus 3 pi over 2, and so on. So generally, if you are to write the one for yn, so yn would be equal to an sine of ax plus nx over 2. So ideally, if we are to take up an example having that in mind, then we can be able to come up with higher order derivatives. So let's say we take up an example. We have our y being equal to sine of 3x. Then what is our y fifth prime? What is the fifth prime going to be equal to? So following this, we will have 3 raised to power 5 sine of ax, and our a right here is 3x plus nx, so that is 5x, all this divided by 2. And you can simplify this to 243 sine of 3x plus 5x over 2. Okay, let's look at the one for cos. So number 3, let's have our y being equal to cos ax. Then how are the derivatives going to look like? So for cos ax, y prime, differentiating the first time, you have minus a sine ax, which is obviously the same as a cos ax plus pi over 2. Differentiating the second time, y double prime. So differentiating this will give us minus a squared cos ax minus a squared cos ax, and this is the same as a squared cos of ax plus 2 pi. Differentiating the third time, y third prime will give us a cubed sine ax, and this is the same as a cubed. This is the same as a cubed cos of ax plus 3 pi over 2. So ideally, if you are to have y raised to power n, then we would have y raised to power n being equal to a n cos of ax plus nx over 2. So taking up an example, then we should be able to evaluate. So example, given y is equal to 4 cos 2x, then we can be able to evaluate y raised to power 6, which will be 4 into what's our a? Our a is 2, so 2 raised to power 6, and then 2 raised to power 6. And then we have cos of ax, so our a is 2x plus n, our n is 6x over 2. Okay, so this simply becomes 256 cos of 2x plus 3 pi. Which can be simplified further. So if you simplify this, this will be 256 cos of 2x plus pi. Okay. Let's take up y as now algebraic. Let's have our y being equal to x a. So if y is x a, then how do we go about this? What's our y prime? Our y prime will be equal to ax into a minus 1. Our y double prime will be equal to a into a minus 1, and then x raised to the power a minus 2. Our y third prime will be equal to a into a minus 1, a minus 2, x now raised to the power a minus 3, and so on. So our yn will be equal to, so as you can see the way this is going, then our yn will just be equal to a minus 1, a minus 2, all the way up to a minus n plus 1. Okay, x a minus n, which can simply be written as, this right here is the same as a factorial over a minus n factorial x a minus n, where a is a positive integer. So if we are to take up an example, y is equal to 2x raised to power 6, then what is our fourth prime? So the fourth prime will be equal to what? So the fourth prime will be equal to, so as you can see, we have 2 there. We'll write the 2 outside, and then our a is 6. So we'll have 6 factorial, all this divided by 6, minus our n is 4 factorial, and then x is raised to the power a minus n, which is 6 minus 4. So evaluating this will give us 720 x raised to the power 2. Okay, number 5, let's have our y being equal to sine hyperbolic ax. Then what's our y prime? So our y prime will be a cos hyperbolic ax. Our y double prime will be a squared ax our y third prime will be equal to a cubed cos hyperbolic ax, and so on. And so on. Now, since it's not periodic, now, since sine hyperbolic AX is not periodic, it is more difficult to find a general statement for yn. However, this is achieved by the following general series. So the general series is y of n is equal to an over 2 Okay, so that's the general statement, that general series that we use for the sine hyperbolic of AX. So for example, if we are to have our y being equal to sine hyperbolic 2x, then we are to get y fifth prime, then this would be equal to, so identifying our a is 2. So putting it back into the formula, we'll have 2 raised to power n. Our n is 5. All this divided by 2. All this into 1 plus minus 1 raised to the power n, and our n is 5. Then sine hyperbolic of ax, that is sine hyperbolic of 2x, plus 1 minus 1 raised to the power 5 cos hyperbolic now of 2x, which simplifies to 2 raised to power 5, that's 32. So this is going to give us, okay, so if you simplify this, this is 32 over 2, and then sine hyperbolic of 2x. This is 1 minus 1. This will give us 0 over here. This will be 0. Then we have sine 2x besides it. And then on this other side, 1 minus minus. So that will be plus 2. And then cos 2x. Okay. So this simplifies to, this is 0, 32, 2. So this will be 32 cos hyperbolic of 2x. 32 cos hyperbolic of 2x. Okay, let's go on to number 6. So number 6, let's have our y being equal to cos hyperbolic of ax. So y prime is a sine hyperbolic of ax. Y double prime is a squared cos hyperbolic of ax. Y third prime is a cubed sine hyperbolic of ax. Now, since cos hyperbolic of x is not periodic, it's also more difficult to find a general statement for yn. However, it is achieved by the following general series. So you note that cos hyperbolic is also not periodic. So basically finding a general statement. So note cos hyperbolic ax is not periodic. So generally finding so it is achieved by the following general statement. So yn is equal to an over 2 into 1 minus 1 raised to the power n sine hyperbolic of ax plus 1 plus minus 1 raised to the power n cos hyperbolic of ax. Okay, so in a similar manner, if you're given a value for, let's say, example, y is equal to 1 over 9 cos hyperbolic 3x, then you're being told to get the value for y7. So following the formula, we have, this is 1 over 9, a raised to power n. So our a is 3. We have 1 over 9 out here, then 3 raised to power 7, all this divided by 2 into bracket 1 minus 1 raised to power n. Our n is, so our n right there is 7. Sine hyperbolic of ax. So our sine hyperbolic of our a is 3x plus 1 plus minus 1 raised to the power 7 cos hyperbolic of 2x. Okay. And this, if you evaluate, it basically simplifies 2. This will simplify 2. 1 over 9, 3 raised to power 7 over 2, 2 sine hyperbolic of 3x, which is the same as 243 sine hyperbolic of 3x, if you simplify correctly. Finally, the last function that we are going to look at is y is equal to ln ax. So if y is equal to ln ax, what is our y prime? Our y prime, the derivative of this will be 1 over x. What is our y double prime? Our y double prime will be equal to minus 1 over x squared. And our y third prime, if you differentiate this, you'll get 2 over x cubed, and so on. So in general, yn will be equal to minus 1 raised to the power n minus 1 into n minus 1 factorial over xn. So for example, if we are to have y is equal to ln 5x, and we are asked to get the sixth prime, then following the formula, we will have minus 1 raised to the power 6 minus 1, and then n minus 1 factorial, so that is 6 minus 1 factorial, that is 5 factorial, all this divided by x raised to power n. So all this divided by x raised to power 6. And this is going to give us 5 factorial is 120, 6 minus 1 is 5, which will give us minus. So here we'll have a minus, and then we'll have 120, all this divided by x raised to power 6. Okay, so that's about it, guys, for the higher order differential coefficients as series. So you guys can do exercise the next exercise for practice and see if you can be able to